Hi everyone, this is the final episode of the warehouse modeling um, using FCalc from RCalc. Uh, you can click on the RCalc Learning Center to look at video number 1 and 2. The third video, which is this one, will be uploaded to this page after we finish recording. In the previous episode, we've set the structure, modeled the structure, and looked at the moments and deflections and made sense of the results. In this episode, we will proceed into reviewing what is happening. So that is the structure that we've been working on. We've got UBs for 60 UBs, 67 kilos on the rafters, 150 UCs, 30 kilos in this direction. And then there will be purlins every 1.2 meters from LISA, between which the color bond or roof sheeting will be spanning in this direction. So, and you've got the lateral stability is maintained through the moment action on this direction and through the braces and the roof trusses on the other direction. So I'll click on analysis. While this one is running, we can look at what we've got now. We've noticed on the previous one that we've had high deflection here. So the span is 28 meters. So, and the deflection from dead load is 92. So 28,000 divided by 92 is 300. Span upon 300 is the deflection. Probably the number is not too much, given that we are talking about industrial structure. But let's say you've got a false ceiling and articulation for the finishes, so that number won't be acceptable. We need to look for techniques or a way to mitigate or alleviate that deflection. We've got also at the moment being 228. We can verify this number by just punching WL squared over 14 here at the eve, because like if you have full fixity will be WL squared over 24, and in the middle will be um, the difference by WL squared divided by 8. So the dead load deflection, we're looking here, if we are saying in 2892, you've got beams on way, which is 67 kilos by the total line load per beam, which was broken in the previous episode, multiplied by the 92, which is the total deflection. So dead load deflection is 17 millimeters. And you have also the SDL deflection becomes 92 minus 17 becomes 75. So the SDL deflection, superimposed load, which is comprising the shearing, purlins, and false ceiling, etc. So I will take the roofing and insulation, divide by total 50 kilos, which is on the first load calculation that we've done here, 50, 49.5. So by doing this, you will be calculating the deflection that happens from the on weight of the steel beams plus the deflection that is happening from the roofing, sheeting, um, together with purlins. So before you install any um, partitions, if this one is going to be an office, for example, or something that will need false ceilings. So that by working this out, so our deflection is 32 coming from permanent loads, which is 34% of the dead load deflection, net deflection. Now, what do we do there? If I want the false ceiling, or doesn't have, like, after we apply the false ceiling loads and let's say went downward or live load, you will get extra deflection over the own weight, that is 60 mil. You might have a problem with the partitions within that industrial structure. If there will be partitions, which is a hypothetical scenario that we're looking at, then we need to mitigate that deflection 60. Let's say somebody's saying the manufacturer for a Hebel or for stud walls won't accept or absorb more than 25, for example, or 30. That can be mitigated by adding a knee brace onto the main frame elements, or propping the rafters to reduce the span and create some sort of a hunch or a moment connection where we've got the central columns that we have here um, in the middle of the warehouse. And we do as well where we've got the valley beam. We will just add that here because that is all of what we can. You can look at this photograph to see how is that might be the scenario. We're modeling something like this essentially. So what do we do there? So by adding those, the deflection becomes at 53 millimeters from dead load deflection. So if we are applying 30% precamber, which is equivalent to the permanent load precambers, if you want to call it, or deflections, then or the own weight related loads, then you will end up with the 20 millimeter less deflection or less impact on the partitions, and then you'll have just like 30 mil or 20 something like that. That will be fine within the finishes. So you will be manufacturing or fabricating the steel structure higher by 20 mil essentially. So and there will be like some sort of detailing. You can add the wedge in a way within those splices of the beam that will create that precamber that will be all absorbed, will go back to zero when you have the on weight of the beam deflecting, and then after you apply the loads of the shearing and the roofing. So that is the way you address the deflection, which is here essentially. So looking at what we have after adding those elements there, the deflection, I've done fine tuning after the calculation, so it's 63 total. So that will be let's say 30% of that 63 times 0.3. So you're doing like some 20-25 mil precamber to address that problem, which is again educational purpose. How do you verify the deflection? So if you're looking at RCalc analysis verifier, if you are short of formula, just like look at common beams, you will find a library of all of the common beams. Let's say you've got fix. So that will be the formula, which is known to everyone, WL to the power 4 divided by 3484 EI, or you can make it equivalent to M, the moment times L squared divided by 16 EI if you don't want to go into those formulas like approximation. And then back to uh, this one, like you just go again, if you want to verify the section capacity, look at steel calculator and go to I sections and then look for the section from the library, um, 46, 67 kilos, 460, you'll find that. So I've taken a screenshot to show that. So they will make perfect sense essentially. If you're just applying the moments, you'll get all of the deflections. This is 99 versus 93 on the original model without any braces. Um, and you can see the comparison between fully fixed and the model. So that is end moment WL squared divided by 12 to divide by 14, for example, and here midspan and so on. But just know that the formula won't be exactly working when you have a roof pitch because you've got axial load, so things will tend to be slightly less than hand checks. All right. So finishing with the theory, I'll be looking at the design now. So after I've assigned all of the elements and run the analysis, there is one thing that you need to do, like you need to provide or build the basic load combinations simply by adding the name there, insert, and select the load combination and put the multiplier. So I've created 6 load combinations for dead on live, wind, and gravity, wind and gravity and live. So those are like very basic, and they should be sufficient because the structure is symmetric, so you don't need to apply minus, plus, when, etc. Again, that is for educational purpose. Um, Now, you go to design menu and then click on, if I just stop the extrusion and then go design, steel design, and click on AS 4100. First of all, you need to run the analysis. Again, keep looking at what is happening here. So that is telling you which load case is being analyzed at this time. So now 304, you've got dead load, live load, and when loading. Sometimes the server uh, won't respond. So if this happens, like click on analyze again. So to repeat the analysis shouldn't be taking long. Case 204, 304, and 404. So finish processing the analysis. Deflection contour is showing there. So you go design, still design, AS 4100. So now the engine is now designing for each and every load combination, 3 of 6, 4 of 6, 5 6, and 6 of 6. So now let's see what will be shown. So now we've finished the analysis. It says you've got 386 members, 226 pass, 160 fail, and it will tell you which load combination is the critical in this scenario. Most of them are under gravity, some of them are governed by wind, and so on. So let's see what is happening with those failing sections. So if you click on this one, you've got the beam is for 67, and it says so the length of the element is automatically determined by the structure about axis y of local axis y, sorry, 3 3, which is this about the strong axis, because this one is spanning from here all the way down to here. There is nothing preventing it from bending downwards, but sidewise it is spanning 5.6. Now the lateral torsional buckling length is probably the reason why you've got it failing. So let's look at, you can look at the steel calculator as well and try to put the same span, which is then you won't get it working under bending moment. This is a very useful app if you wanna not look at the PDF catalogs, so that will help you navigate the Australian sections library. So what I'm gonna do there, I'm closing this one, and then I will be going to select menu, which is select items by section. So you take uh, this one, right, and this one. So you've got two types of sections that we need to select, the rafters essentially. Uh, and then you go to design. So I'll just like unlock the analysis for now. Although like you don't need to unlock the analysis if the design is done, but just to do the design things in one go. So select, or first of all, select by section, UB, select, design, select, and then you go set LTB length. Now we've got the purlin space at 1.2 as we agreed. So we'll make that at 1 point, let's say 2.4, not every purlin, every second purlin, there will be fly braces. Um, it is now, yeah, it is now designing again after this edit. So let's see what is happening after that design. And you can know that design becomes faster when the sections are uh, um, less struggling. So you see the sections that we've edited, they are all becoming green now. So let's select the next one, which is 82. Select, design, steel, LTB at 2.4, and say OK. So I will repeat the analysis again, or repeat the design engine. 4 of 6, 5 of 6, and then 6 of 6. So now you've got all of the rafters, seem fine. Now you've got, let's see what is happening with those elements north, south of the page. So if I'm clicking on this one, you've got those sections spanning 6 meters between the elements. So there it says the effective length on the horizontal is 6 meters, but that is not the LTB length. That is the effective length as a column. It is 36, so it's spanning from here all the way down. So the program understands that it all bends under compression, kind of between this point and that point, which is a case that you need. It won't happen because you're restraining that section throughout. So that said, I will be selecting all of those 150 UCs, and then I go design, steel, and override effective length. You just need to do one, so it will read it between the nodes. Now what happens, design will repeat again. It's now running 4 to 6, 5 of 6, and 6 of 6. So we've just finished designing 386 elements in this structure. All of them are passed. Highest utilization is 97.7.9. So you can look into those, zoom into those if there will be a problem later. But overall picture, you've got it all designed. If you want to have a look at any of those, so let's see this one. You've got it will tell you what is the member name, governing load scenario, LTB length, utilization, and it will tell you what is happening from the analysis. So you've got the moments uh, um, or the utilizations under axial, under moments. So that is governed mostly by moment about gravity direction. Those are the capacities under those supporting conditions for that section. They will be exactly matching with the steel calculator. Because we are using the steel calculator calculation engine essentially, and it will highlight where is the highest utilization essentially, which is at the beginning of this section, um, and that's it. So final thing, if you wanna, for example, just for fun, I will unlock the model and then select, let's say, all of the, let's say one column here. Let's say take that column and then assign a concrete section, a hypothetical scenario. You've got 50 MPa, call it 500 by 500 concrete section, which is here. You can look at extrusion. So that is the concrete section in question. And now we repeat the analysis because stiffness have changed to see what is being attracted to that section and how we design it to the 3600 Australian standard for concrete. Finishing analysis. So now we go to, once analysis is done, so we go concrete design and then design columns to AS 3600. So you've got the column which is divided into segments because I wanted to create that support for the beam to reduce or the knee brace to reduce the deflection. So click on any of those. So you will get a design memo telling you what is happening there. So that is the section MPa, what is the required reinforcement to withstand those actions. It will draw the interaction diagram. So this one is largely governed by this direction because you've got the moment being 400, the magnified moment after multiplying by delta B, which is magnifier for slenderness. If you want to have a look at this column on its own, and which load combination is this, 1.2, 1.5. So let's go 1.2, 1.5, and let's look at N. So hover the mouse here, and at the bottom is 160-ish, let's say, or here we are talking about 148 because that is the segment that we are designing, which is this one. Um, you look at M33 here, of that segment is 360 or if I zoom or maybe switch on the values and look at it. So you've got, what is it? 400 here, which is the number, this one there. 393 goes down to 400. And this concludes the example. Thank you.